All right, welcome. This is Ralston Valley High School AP Chemistry's lecture series. We are looking here at Chapter 5, Lecture number 3, in which we'll discuss non-ideal gases. Let's get started. In this lecture, we're going to be discussing species we refer to as real gases. These are gases which exist under non-ideal conditions. Recall on our previous discussions of gas behavior, we've talked about specifically the ideal gas law. And when we talked about ideal gases, we're really talking about gases which essentially follow the assumptions set forth from our discussions of kinetic molecular theory. Now, as we discussed kinetic molecular theory, remember those ideas we put forth were useful lies that we tell ourselves that helped us to simplify our calculations by making use of some approximations that made the math a little bit easier. And in most instances, the assumptions that we made in kinetic molecular theory were not so untrue as to cause undue oversimplification of the behavior of gases. But for some real gases, there are deviations from what we might expect based upon those assumptions we made in our discussions of kinetic molecular theory. In particular, recall that part of the tenets of kinetic molecular theory was the assumption that gas molecules themselves are essentially volumeless points in space. Now, recognize that fundamentally, I know that to be an untrue statement. Gases are matter, and everything that's matter has both mass and takes up space. Because the distances which separate gas phase molecules tend to be very, very large compared to the size of the gas molecules themselves, in most cases, making that assumption that the particles themselves were volumeless didn't cause undue changes to the actual calculations we would make using our ideal gas equation. But sometimes that might not necessarily be true. The more densely packed together our gas phase molecules are, the more volume those gas molecules actually occupy, and therefore the less true that assumption we made becomes. Likewise, gas phase molecules that are larger in space themselves, that is, say, large molecules like, say, xenon hexafluoride, will clearly act less ideally because they truly do occupy more space than smaller molecules or atoms like, say, elemental helium. Likewise, we also made an assumption in our discussion of kinetic molecular theory that gas molecules do not exert either attractive or repulsive forces upon one another. This also, again, in most instances, was a valid assumption to make because, again, as the distance separating those gas molecules tends to be very, very large, and because forces of attraction or repulsion via Coulomb's law generally fall off as the inverse square of the distance separating those particles, because the particles themselves are far apart, that would imply that those forces of attraction or repulsion between those charged particles would therefore be generally minimal. This becomes, however, less true when we deal with maybe, say, highly polar molecules, because we know that the attractive forces that exist between molecules are intermolecular forces of attraction. Molecular species that are highly polar would therefore be likely to exhibit meaningful attractive or repulsive forces depending upon the strength of those dipoles. So therefore, again, those assumptions that we made that those forces of attraction and repulsion were non-existent becomes less true for different species. So over our next couple of slides, we'll be examining how some of those assumptions that we made were perhaps an oversimplification, and how we could then change our calculations to account for the fact that some of those assumptions really, truly, fundamentally are not themselves true. So to summarize, gas phase systems which exist with stronger IMFs would therefore be less likely to follow the rules we have applied for ideal gases. And then for gas phase species that exist with either higher pressures or higher densities, that would imply the particles occupy more volume and are therefore more likely to, again, not follow the behaviors described by the ideal gas law. Likewise, gas phase species that exist at low temperature would be said to be behaving less ideally, because at low temperatures, gas phase molecules would be on average traveling slower, which would imply a greater tendency to interact between the same two particles as they would spend more time in the vicinity of one another. And that would therefore cause them to exert attractive forces for longer periods of time, which might make them, again, behave in a less ideal fashion. So with these kind of general overview, let's have a look on our next slides about how we might modify that ideal gas equation to account for the real behavior of gases. All right, for the first modification we're going to make to the ideal gas law, we're going to take a look at a volume adjustment to account for the real behavior of gases. Because again, in the tenets of kinetic molecular theory, we said that gas particles themselves were essentially volumeless points in space, we recognize again that that's a false statement. And the more space occupied by those gas molecules, the more false that statement becomes. Now, there are really two different ways we might expect to see the volume occupied by these gas molecules differ. Either number one, the gas molecules could be larger on a per particle basis, or number two, there could be more of the gas molecules present within the system. So consider here an initial sample that we have of, let's say, helium gas at a very, very low density. Those helium gas atoms are very, very small on a per particle basis. And number two, if they're at low density, that means there's not many of them present, implying, therefore, the amount of available space within the container to any particular individual gas phase helium atom is actually very, very large, essentially equal to the volume of the container. Now, contrast this with an alternate gas phase system in which we had a high density of xenon atoms present in our system. Each individual xenon atom is much, much larger on a per particle basis, and additionally, at high densities, that would imply there's lots of those xenon atoms present, implying, therefore, the actual amount of available space any one individual xenon atom could move to is significantly smaller than the overall total volume of the container. So from this idea, we can see that the volume available to a real gas is essentially equivalent to the volume of the container minus essentially a factor which accounts for both the number of gas phase particles present in the container, as well as a secondary factor which is proportional to the actual size of space occupied by an individual gas phase particle. So we get this equation here that the volume available to a real gas is equal to the volume of the container minus n, the number of particles present, times b, which in this case is what we refer to as the van der Waals volume constant, which is dependent upon the specific identity of the particle that we are dealing with. I've given you here on the right side of our page a series of values for that gas constant b in units of liters per mole. Notice here that the very, very small species, such as helium and neon, have very, very small values of that constant, implying these species are less likely to impact the available space available to a gas-phase molecule due to the small size of the individual particles themselves. That is in contrast to the larger particles, like let's say particles of chlorine or of methane, with larger values of this van der Waals volume constant, we would expect to see, therefore, a greater deviance or departure from the volume of the container as we look at the volume available to any real individual gas particle within our system. So we can now essentially adjust for the size of the particles as well as the number of particles which are present within our system by using our adjustment factor here in the equation described. So with the volume of a real gas now described by our equation, on our next slide we'll have a look at how a real gas might experience a difference in pressure as compared to an ideal gas that follows the stipulations of kinetic molecular theory. So now that we've seen on our previous slide how the volume available to a real gas differs from the idealized volume predicted by kinetic molecular theory, on this slide we'll now have a look at how the pressure of a real gas might differ from that predicted by kinetic molecular theory. Now note here a couple of ideas. Number one, as the density of a gas increases, that would imply a greater amount of collisions as well as close encounters between gas phase molecules. The closer together those particles are on average and the more frequently they collide with each other, the more of a role intermolecular forces of attraction are going to play in terms of the interactions between our gas phase particles. And noting that one of the tenets of kinetic molecular theory is that we assume the attractive or repulsive forces that exist between gas phase particles are essentially inconsequentially small, that implies therefore that species at higher densities, where the pressure is higher, would probably deviate more from the idealized behavior predicted by our ideal gas law. Now, continuing this same line of thinking, species which exhibit stronger intermolecular forces of attraction, either by having very, very strong dipole moments or by being larger molecules with stronger London dispersion forces, would likely also be more attracted to their neighbors as well, and this attraction is going to affect, again, the pressure exerted within a gas phase system. To consider why, imagine how those gas phase molecules in essence exert pressure. Pressure results from the collisions between the molecules in the gas phase and the walls of their container. If we have stronger forces of attraction between particles due to either an increase in the density and therefore pressure of the system, or due to an increased strength of intermolecular forces of attraction between particles, there would be a net attraction towards the other gas phase molecules, which would in essence essentially soften the collisions and rate of collisions between the particles and the walls of their container. And in effect, the resulting outcome of this idea would be that the observed pressure would be smaller than the pressure predicted by the tenets of kinetic molecular theory. Now, we're not going to spend time during this lecture deriving the equation to describe the pressure observed by a real gas in comparison to the idealized pressure predicted by the ideal gas law. However, we will give you the equation and then describe why it is that this equation makes logical sense given the conversation we've just had. So the equation for the observed pressure of a real gas would be equal to nRT, that is moles of gas, times the gas constant R, times the temperature T, divided by a factor volume minus NB. That essentially is the corrected volume factor which we saw on our previous slide. And then from that, we're going to now subtract a pressure correction factor, which is going to be given by this factor AN squared over V squared. Now, the N squared over V squared essentially is proportional to the density of the system, that is moles of gas particles N over volume V in our system. So long story short, that would imply at greater densities, we should expect to see a larger deviation from the predicted ideal pressure from the ideal gas law. And then the other factor present in this correction factor for the pressure is a constant A, which is what we call here the van der Waals pressure constant. That van der Waals pressure constant in units of atmosphere liter squared per mole squared essentially is again a factor which is going to account for the differences in the intermolecular forces of attraction between species. I've again given you a table which describes those values of that van der Waals pressure constant on the right side of our page here. Notice that species that are incredibly small, like say helium with a small, relatively unpolarizable electron cloud, are going to, in general, deviate by a very small amount from idealized behavior because those particles themselves experience very, very weak intermolecular forces of attraction between particles. Now, that's in contrast to other species which we might find with a much higher value of this constant, species like, let's say, chlorine, with a value of 6.49 atmosphere liter squared per mole squared, or like water, with a value of 5.46 atmosphere liter squared per mole squared. And let's understand why these species like chlorine and water have much larger values of this van der Waals pressure constant. Chlorine itself is a much, much larger molecule with a significantly larger cloud of electrons, which is therefore a more highly polarizable electron cloud, and we would therefore expect to see much stronger London dispersion forces between molecules of chlorine than we would between individual helium atoms within a gas phase system. Water, although it's a small molecule, is a highly polar molecule, which we know when very, very close to other water particles might exhibit very, very strong dipole moments, which we would consider to be, in essence, hydrogen bonds. So due to the much stronger intermolecular forces of attraction between these species would be expected to deviate by a much greater amount from the predicted idealized pressure within a gas phase system predicted by the ideal gas law. So looking at that calculation again on our equation for the observed pressure, notice here that the stronger the intermolecular forces of attraction, as indicated by the larger value of the van der Waals constant, we'd expect to be subtracting then a larger pressure correction factor from the value nRT over V minus NB, leading to a lower observed pressure, as those gas molecules, in essence, are going to again attract one another towards the center of the gas system, away from the edges of the container, and in effect, soften the blows as those gas particles collide with the surfaces and decrease the pressure. Now, likewise, we can also note here that at greater densities, the factor N squared over V squared would also be larger, implying therefore at greater densities, we would expect to see stronger attraction between particles because they would spend more time close together, and again, a greater deviation from the idealized pressure predicted as we see that factor AN squared over V squared become larger, leading to a lower observed pressure overall. So it makes logical sense, even though we're not going to go ahead and derive the entirety of that equation, about how it might actually function in real-world applications. Now, it might be useful for us to rearrange this equation, and as I do so, I'm simply going to add that factor of an squared over v squared to both sides of the equation, and then multiply by the denominator, which was again v minus nb. And as I do so, you'll notice this equation should look very, very familiar at that point. It becomes now the observed pressure plus that conversion factor of an squared over v squared times v minus nb is equal to nRT. And what this really looks like to me now is essentially a modified version of our ideal gas equation. That is, a corrected pressure, that is P observed plus that correction factor, times a corrected volume, that is the volume minus NB, is equal to nRT. And this really now describes to a more correct fashion the actual observed behavior of real gases in the world around us. All right, so on our final slide, we'll take a look at how we can use this derived equation in order to make some calculations to predict the behavior of gases that are more real rather than idealized. Moving on to our final slide. All right, so for our final slide here, we're going to take a look at an example problem in which we're being asked to compare the pressure exerted by a gas as predicted by the ideal gas law with the pressure predicted for a gas under real conditions. Now, in terms of this problem, we'll have a look at the given values. We're being asked here to calculate the pressure exerted by 0.100 moles of xenon gas at a temperature of 298 Kelvin in a 1.00 liter container, again, first assuming ideal behavior. So let's do that section of this first. Identifying my variables here, again, I've got moles, which in my equation for the ideal gas law is N of 0.100 moles, a given temperature T of 298 Kelvin, and a given volume V of 1.00 liters. And note again here, I need a value of the gas constant R, which I'm going to choose to use in units of liter atmospheres per mole Kelvin. That constant R is, again, from your gas laws days, 0.08206 liter atmospheres per mole Kelvin. And again, we're going to be using here our ideal gas equation, which was PV equals nRT. Rearranging this equation to solve for the pressure yields the expression pressure is equal to nRT over V. And now I can simply go ahead and plug in my given values into our equation. As I do so, I get the moles of gas, 0.100 moles, times the gas constant R of 0.08206 liter atmospheres per mole Kelvin, times our temperature T of 298 Kelvin, all divided by the volume V of our system of 1.00 liters. And as I do so, note here that units cancel nicely for me. I see moles and 1 over moles canceling out. I see liters over liters. Those will also cancel. And I notice Kelvin and 1 over Kelvin both also exist in my numerator, implying therefore the units should turn out to be in units of atmospheres. Plugging this into my calculator, I predict a value here under ideal conditions of, looks like 2.45 atmospheres for this xenon gas. Now again, this is assuming ideal behavior. Let's now use the equation given to us on our previous slide to describe the observed pressure of a real gas. That calculation was, again, the observed pressure should be equal to the value nRT divided by, in our denominator, the volume minus NB minus the correction factor here for the pressure of AN squared over V squared. And we'll have a look here. We need a couple more pieces of information to complete this. Recognizing again that this is xenon gas, I'm going to go back to my previous slides and check real quick here to find the values of those van der Waals constants A and B. The volume correction constant B given to us on the previous slide is a factor of, looks like 0.0511 liters per mole for xenon gas. And the pressure correction constant, that is the value A on our previous slide, was given to us as 4.19 atmosphere liters squared per mole squared for that van der Waals pressure constant. And at this point, I now have all the information I need to plug all of this data into my equation. So again, the observed pressure would be equal to the moles of gas, N, which was 0.100 moles, times our gas constant R, which again was 0.08206 liter atmospheres per mole Kelvin, times the temperature T of 298 Kelvin, all divided by, in our denominator, the corrected volume here of 1 liter minus the value NB, which in this case would be 0.100 moles, times the van der Waals volume correction constant here of 0.0511 liters per mole. And then we're going to subtract from that the factor again, AN squared over V squared, which would be our van der Waals pressure constant of 4.19 atmosphere liters squared per mole squared, times the number of moles N, which was again 0.100 moles, that gets squared. And then our denominator, we'll divide that by our volume of 1.00 liters, again, which gets squared. Now this is a big mess of math to plug into your calculator here. Make sure you pay attention to your order of operations as you do so, and parentheses are your friend in this instance. But note here that units are going to very nicely cancel out for me here. I notice that I have moles and inverse moles in my numerator here canceling out. We also see values of Kelvin and 1 over Kelvin in the numerator. And then our denominator here, let's see, we've got, moles times 1 over moles, so those will also cancel out. And I end up then essentially with liters minus liters in that denominator, which will yield units of liters, which then should cancel out with the liters in the numerator as well. So the only thing out of that whole first part of our expression that doesn't cancel out are units of atmospheres, which is great because again, we're looking for a pressure. And again, then in our pressure correction there, that is the AN squared over V squared. Let's see, we've got moles squared and 1 over mole squared in our numerator, which cancel out. And then it looks like we've got liters squared over liters squared, which will also cancel, again, yielding units of atmospheres. So this whole gigantic mess, we're now going to plug into our calculator. And when I plug it in, I get a value that comes out here of 2.41 atmospheres. Now, importantly here, folks, notice that there is a variation from the predicted behavior with our ideal gas law, as opposed to the pressure predicted by our real gas equation. And note that in particular, the pressure predicted by our real gas equation is moderately smaller than the pressure predicted by our ideal gas equation. Again, giving some mathematical quantitative evidence to support our idea that the pressure exerted by a real gas should be smaller than the pressure observed by an ideal gas due to, again, that net attractive force towards the center of the gas phase system due to those intermolecular forces of attraction between particles. And again, this deviation, although it is small, is meaningful within the number of significant figures which we've recorded, meaning therefore, again, xenon gas does not exactly follow the ideal gas equation as we have shown you from your first year chemistry class. All right, so that is it for real gas behaviors. Now, importantly, on the actual AP test, you are very exceedingly unlikely to be asked to actually make calculations of the pressure of a real gas system. So quantitatively speaking, this is not generally covered on the AP test. That being said, there's very much an idea which is covered in a qualitative sense. So understanding the ideas of kinetic and molecular theory and understanding qualitatively speaking how real gases should be expected to deviate from ideal behavior is something that very much will be covered on the AP test. And having a mathematical foundation for understanding why this works the way it does is a very useful tool. So again, you will not find these equations on your AP Chemistry equation sheet, but we'll have you work a couple of example problems within your homework assignments just to make sure you have a mathematical basis from which you can understand this, which should help to enhance your qualitative understanding as well. All right, thanks so much for listening, and we will see you on your next lecture.